Previously, we discussed the idea of a vertical asymptote, or essentially what happens when a function goes up very, very quickly, or as we say, goes to infinity towards a particular limit. Like say, for example, as x approaches 0 from the right, our function goes up to infinity. But certain times, and what I said before is that often is related to division by 0 in an algebraic setting. And there's actually other instances that can cause asymptotes in other mathematical functions that we don't need to worry about for the purposes of this class. But sometimes actually dividing by 0 doesn't result in an infinite limit. Sometimes it can result in something else. And this is another thing, which is a discontinuity called a hole, which let's go ahead and look at. So let's again return back to the packet. It says, let g of x equal x squared minus 9 divided by x minus 3. Answer the following questions. So start off by saying, what is g of 3? What does this mean about the domain of the function? So let's just go ahead and try plugging it in and see what happens. Well, if we plug in 3, I would get 3 squared minus 9 divided by 3 minus 3. And of course, that's 9 minus 9 on top, which is 0, and 3 minus 3 on bottom, which is 0. And remember, 0 is allowed to be in the numerator of a fraction, but never in the denominator. So what this is an undefined value. So this is undefined. And remember that implies that 3, this value here, this is not a legal input in the function when we're talking about the real numbers. So we often say that this is not in the domain. Or returning back to algebra, if we were talking about the domain of this function, well, it's undefined when x is equal to 3. And so we might often phrase it this way: x cannot be 3. Or if we're using interval notation for the domain, we'd see that x can be any number from negative infinity to 3 or 3 to infinity. But anyways, that's a review of the idea of domain. But essentially, if we were to graph this as well, let's use our calculator to help us along. Again, I would recommend using parentheses around both the top and the bottom of our, this is called a rational function because it's a fraction of polynomials. But let's go ahead and see what this looks like. If we graph this, it's kind of interesting because it actually just looks like a linear function. It looks like a straight line. And if you plug some other numbers into this, like say we plug in 0, we would get negative 9 over negative 3, which would be 3. So I would have a y-intercept of 3. If I plug in 1, and again, we could use a trace feature to do the math for us on our calculator, I'm going to get 4. If I plug in 2, I'm going to get 5, and so on. And what we see is actually, this appears to just be a normal linear function. But what's interesting is, let's say we were to plug in 3, because what we concluded by examining what happens at 3 is that's undefined. And notice that your the calculator here has nothing. It just says y equal blank. And this is always an indication for an undefined value or something which is not part of the domain. Or if we actually look at the table here, it'll actually come up with an error in your calculator. And that's usually indicative of division by 0, or there's other errors that can occur, mathematically speaking. But basically, why I wanted to bring this up is because when I'm tracing along, it looks perfectly fine, like there is no gap or there's no hole here. But technically, there's an undefined value at 3, which would be right there along this. But otherwise, every one of those points is defined. So summarizing here, this function looks and is a completely linear function. But what happens is there's a hole right in the middle at 3 due to this undefined value. However, we can still examine the limit of this function because every other value appears to be just fine. The only undefined value occurs when the denominator could be 0, which only would happen if x is exactly 3. But let's see what happens if we look at the limit. Because while the value of the function is defined, it doesn't mean the limit doesn't exist. So looking at the right-hand limit, it says find it 2 ways graphically and numerically. Well, if we look at this function from the right-hand side, it appears as though it's going to be headed towards that point, headed towards 3. Well, not 3, but remember, with the limit, you always give the y value. Because I'm targeting at when x is 3, what would happen to the value which is always associated with y. And since I had 0, 3, 1, 4, 2, 5, this would be the point 3, 6. So really this y value here is 6. Even though what it gives me is 0 divided by 0, which is not defined. But on the right-hand side, it appears to be headed towards the point along the line. And again, what I could do is even take my cursor and trace along here. If I'm getting closer and closer to 3, it appears to be headed towards 6. And same with the left-hand side, as I'm getting closer and closer on the left-hand side limit there. So I'll go ahead and write that down here. The right-hand side limit appears to be 6 towards 3. And as x gets closer and closer to 3 from the left, it appears to be getting closer and closer to 6 as well. But again, I had that problem at specifically 3 where it was undefined. So anyways, what I wanted to mention here is both the left and the right-hand limit are both headed towards 6 graphically. And also numerically, if we try plugging in, say, 2.9 or 2.99, you'll notice that it gets sufficiently close to 6 from the left-hand side. And from the right-hand side, say 3.1 or 3.01, it's also getting sufficiently close to 6. So either way you slice it, both directions is headed towards 6. So we'd say that the general limit of this function is headed towards 6 as well. Even though it's undefined in the function, that's okay. As long as both limits agree, they're headed both towards that point. And again, in math, we often refer to this as a hole. This function looks just like a line. For all intents and purposes, it is a line. It's linear, except it's got this hole. It's got this problem area, which is caused by the division of x minus 3. And actually, another just sort of wrap-up topic from algebra, one thing that we do in with functions such as this is sometimes we might say, you might be faced with the question which is simplify this expression, right? In which case we could use our factoring principles, right? Because the top is a difference of squares. The top would factor as x plus 3 times x minus 3. And if we first factor our polynomials, we could then look for common factors. Since it's a fraction, anytime it has a common factor, those would cancel by the rule of fraction simplification. And remember, you can't cancel like this. That's not allowed because you can only cancel common factors. You can't just cancel random stuff. I digress. But basically, what I would end up with if I were to perform that simplification is a simplified function, which indeed is linear. And that's actually what this line is going to graph. Notice it has a y-intercept of 3 and a slope of 1. It's exactly the line. However, the thing was this part of the algebraic expression, the original g function is this. This function and this function are not identical. The difference is this one has a hole in it. And that's really the only difference. And it's why this is kind of interesting, and it's why this limit is a little bit strange. But what I wanted you to notice about this is the limit actually works for the simplification. If I just plug in 3 into the simplified version of this, what that ends up giving me is 6. And this is kind of an introduction to a different approach of limits, which is the algebraic side. We're going to come back to that in the next section.